Lesson 11. Welding of dissimilar metals and exotic materials. Hello folks, welcome to the lesson on welding of dissimilar metals and exotic materials. In this lesson, we will explore the fascinating world of welding dissimilar metals and exotic materials. We will cover the challenges and techniques involved in welding different types of metals and alloys, delve into the specifics of working with exotic materials like titanium and Inconel, and discuss advanced welding techniques and safety protocols. This lesson is designed to provide both theoretical insights and practical knowledge to enhance your understanding of these complex processes. Welding of dissimilar metals and alloys. Understanding dissimilar metal welding. Welding dissimilar metals involves joining two or more metals with different compositions. This process presents unique challenges due to differences in thermal expansion, melting points, and metallurgical characteristics. Common examples include joining stainless steel to carbon steel, aluminum to copper, or even titanium to nickel-based alloys. Challenges: thermal expansion. Differing expansion rates can cause distortion or cracking. Melting point differences. Varying melting points lead to uneven heat distribution. Metallurgical incompatibility may create brittle or weak zones at the joint. Solutions. Proper filler material. Choose a filler material compatible with both metals to create a stable joint. Preheating or post-welding heat treatment. These techniques help minimize stress and potential cracking. Advanced welding techniques employ methods such as friction welding or explosion welding for high-stress applications. Welding of exotic materials, for example, titanium, Inconel. Welding exotic materials such as titanium, Inconel, and other high-performance alloys requires specialized techniques due to their unique properties. These materials are often used in aerospace, chemical processing, and other high-demand industries because of their excellent strength-to-weight ratios, corrosion resistance, and high-temperature stability. Titanium welding. Challenges. Titanium is highly reactive with oxygen and nitrogen at high temperatures. Shielding gas. Use inert gases like argon to protect the weld pool from atmospheric contamination. Cleanliness. Ensure surfaces are free from contaminants to prevent weld defects. Inconel welding. Challenges. Inconel's high nickel content can lead to cracking if not properly managed. Heat input control. Use precise heat control to avoid excessive grain growth. Post-weld heat treatment. Reduces residual stresses and improves mechanical properties. Advanced welding techniques and safety. To address the complexities of welding dissimilar and exotic materials, advanced welding techniques are often employed. These methods provide greater control over the welding process, resulting in higher quality joints. Laser welding offers precise control over heat input, making it ideal for thin sheets and intricate designs. Electron beam welding provides deep penetration with minimal distortion, suitable for thick sections. Friction stir welding, a solid-state process that reduces porosity and enhances joint strength without melting the materials. Safety considerations in advanced welding. Working with advanced techniques and exotic materials requires stringent safety measures to protect both the welder and the work environment. Personal protective equipment (PPE). Always wear appropriate PPE, including welding helmets, gloves, and protective clothing, especially when dealing with high temperatures and reactive materials. Ventilation. Ensure adequate ventilation to mitigate exposure to fumes and gases, particularly when welding materials like titanium that produce hazardous byproducts. Equipment maintenance. Regularly inspect and maintain welding equipment to prevent malfunctions and ensure a safe operating environment. Training and certification. Continuous training and proper certification are essential in handling advanced welding processes safely and effectively. Executive summary. Here's a summary of welding of dissimilar metals and exotic materials. Welding of dissimilar metals. 1. Definition: welding of dissimilar metals involves joining two or more metals with different chemical, physical, and mechanical properties. 2. Challenges: Welding dissimilar metals can be challenging due to differences in thermal expansion, corrosion resistance, and mechanical properties. 3. Techniques. Various welding techniques can be used, including shielded metal arc welding small, gas metal arc welding GMAW, gas tungsten arc welding GTAW, and friction stir welding FSW. 4. Applications. Welding of dissimilar metals is commonly used in aerospace, automotive, and construction industries. Welding of exotic materials. 1. Definition: exotic materials refer to metals and alloys with unique properties such as high temperature resistance, corrosion resistance, or high strength to weight ratios. 2. Examples: exotic materials include titanium, zirconium, and advanced alloys like Inconel and Haynes. 3. Challenges. Welding exotic materials can be challenging due to their unique properties, which can affect weldability and joint performance. 4. Techniques. Specialized welding techniques such as GTAW, plasma arc welding PA, and electron beam welding EBW are often used to weld exotic materials. 5. Applications. Welding of exotic materials is commonly used in aerospace, nuclear, and chemical processing industries. Key considerations. 1. Material compatibility. Ensuring compatibility between the base metals and filler materials is crucial. 2. Welding technique. Selecting the appropriate welding technique and parameters is essential. 3. Heat input control. Controlling heat input is critical to prevent distortion, porosity, and other defects. 4. Post-weld heat treatment. Post-weld heat treatment may be necessary to relieve residual stresses and achieve desired mechanical properties. Future developments. 1. Advances in welding techniques. Continued development of advanced welding techniques such as laser beam welding and friction stir welding. 2. New materials and alloys. Development of new materials and alloys with improved properties and weldability. 3. Improved modeling and simulation. Advances in modeling and simulation to better understand welding processes and predict joint performance. Here's a summary of welding of dissimilar metals and alloys. Welding of dissimilar metals and alloys. Challenges of welding dissimilar metals. 1. Thermal expansion. Differences in thermal expansion can cause distortion and residual stresses. 2. Corrosion resistance. Differences in corrosion resistance can lead to galvanic corrosion. 3. Mechanical properties. Differences in mechanical properties can affect joint strength and ductility. Techniques for welding dissimilar metals. 1. Shielded metal arc welding SMAW, suitable for welding thick sections of dissimilar metals. 2. Gas metal arc welding GMAW, suitable for welding thin sections of dissimilar metals. 3. Gas tungsten arc welding GTAW, suitable for welding thin sections of dissimilar metals, especially when high precision is required. 4. Friction stir welding FSW, suitable for welding dissimilar metals without melting. Considerations for welding dissimilar metals. 1. Material compatibility. Ensure compatibility between the base metals and filler materials. 2. Welding technique. Select the appropriate welding technique and parameters. 3. Heat input control. Control heat input to prevent distortion, porosity, and other defects. 4. Post-weld heat treatment. Apply post-weld heat treatment to relieve residual stresses and achieve desired mechanical properties. Examples of welding dissimilar metals. 1. Stainless steel to carbon steel, common in chemical processing and power generation industries. 2. Aluminum to steel, common in aerospace and automotive industries. 3. Copper to steel, common in electrical and electronics industries. 4. Titanium to steel, common in aerospace and chemical processing industries. Future developments. 1. Advances in welding techniques. Continued development of advanced welding techniques such as laser beam welding and friction stir welding. 2. New materials and alloys. Development of new materials and alloys with improved properties and weldability. 3. Improved modeling and simulation. Advances in modeling and simulation to better understand welding processes and predict joint performance. Here is a summary of exotic welding. Welding of exotic materials. Challenges of welding exotic materials. 1. Reactivity. Exotic materials like titanium and inconel can react with air, moisture, and other elements affecting weld quality. 2. High thermal conductivity. Exotic materials can conduct heat quickly, making it difficult to control the weld pool. 3. Low ductility. Exotic materials can be brittle, making them prone to cracking during welding. 4. High cost. Exotic materials are often expensive, making welding errors costly. Techniques for welding exotic materials. 1. Gas tungsten arc welding GTAW, suitable for welding thin sections of exotic materials, especially titanium and inconel. 2. Gas metal arc welding GMAW, suitable for welding thicker sections of exotic materials, especially inconel. 3. Electron beam welding EBW, suitable for welding exotic materials that require high precision and low distortion. 4. Laser beam welding LBW, suitable for welding exotic materials that require high precision and low distortion. Considerations for welding exotic materials. 1. Material preparation. Ensure the material is clean, dry, and free of contaminants. 2. Welding technique. Select the appropriate welding technique and parameters. 3. Shielding gas. Use a shielding gas that is compatible with the exotic material. 4. Heat input control. Control heat input to prevent distortion, porosity, and other defects. Examples of welding exotic materials. 1. Titanium, used in aerospace, medical implants, and high-performance sports equipment. 2. Inconel, used in aerospace, chemical processing, and power generation. 3. Hastelloy, used in chemical processing, power generation, and marine environments. 4. Monel, used in marine environments, chemical processing, and power generation. Future developments. 1. Advances in welding techniques. Continued development of advanced welding techniques such as laser beam welding and electron beam welding. 2. New materials and alloys. Development of new materials and alloys with improved properties and weldability. 3. Improved modeling and simulation. Advances in modeling and simulation to better understand welding processes and predict joint performance. Here's a summary of safety considerations in advanced welding. Safety considerations in advanced welding. 1. Personal protective equipment (PPE). Welders must wear PPE, including helmets, gloves, safety glasses, and fire-resistant clothing. 2. Ventilation. Proper ventilation is essential to prevent inhalation of welding fumes and gases. 3. Fire prevention. Welding areas must be free from flammable materials, and fire extinguishers must be readily available. 4. Electrical safety. Welding equipment must be properly installed, maintained, and operated to prevent electrical shock. 5. Ergonomics. Welders must use proper ergonomics to prevent musculoskeletal injuries. Hazards associated with advanced welding. 1. Arc flash, a sudden release of electrical energy that can cause burns and eye damage. 2. Welding fumes can cause respiratory problems and other health issues. 3. Noise. Prolonged exposure to loud noises can cause hearing loss. 4. Radiation. Exposure to ultraviolet and infrared radiation can cause eye damage and skin burns. 5. Explosions can occur when welding near flammable materials or in confined spaces. Safety measures for advanced welding. 1. Regular maintenance. Regularly inspect and maintain welding equipment to prevent accidents. 2. Proper training. Ensure welders receive proper training on advanced welding techniques and safety procedures. 3. Safety protocols. Establish and follow safety protocols such as lockout, tagout procedures. 4. Emergency preparedness. Have a plan in place for emergency situations such as fires or explosions. 5. Continuous monitoring. Continuously monitor the welding environment to identify potential hazards. Best practices for safety in advanced welding. 1. Follow industry standards. Follow industry standards and guidelines for safety in advanced welding. 2. Use proper equipment. Use proper equipment such as welding helmets and gloves to prevent injuries. 3. Stay alert. Stay alert and focused while welding to prevent accidents. 4. Communicate with team members. Communicate with team members to ensure everyone is aware of potential hazards. 5. Continuously improve safety procedures. Continuously improve safety procedures to ensure optimal safety in advanced welding. Conclusion: welding of dissimilar metals and exotic materials is a complex yet rewarding field that opens up many opportunities in advanced engineering and manufacturing. By understanding the challenges and employing the correct techniques, you can achieve high-quality welds even under demanding conditions. Remember always to prioritize safety and continue learning about new advancements in welding technology to stay at the forefront of the industry. We hope this lesson has provided valuable insights into the intricacies of welding diverse materials. If you have any questions, feel free to reach out for further clarification or discussion. Happy welding! See you in the next lesson. Happy learning, folks!